Welcome to this lecture where we're going to talk about B trees. In this sequence of 4 lectures, we're talking about alternative ways of balancing data in tree structures. And we've talked about splay trees and red-black trees, and in this lecture, we'll talk about B trees. Now, B trees, the purpose of B trees is to deal with data that's so large that it cannot fit easily in main memory. In all of our discussions so far on almost every data structure, we've sort of assumed that we don't have a ton of data to store, but enough that it makes it worthwhile to use a data structure for efficient access. But imagine if we had to store so much data that it would not fit in main memory. This is where B trees really shine. If we had to suppose we had to store and search a terabyte of data, modern computers won't hold that much in memory. Now, a few years from now, if you're watching from when I record this, maybe that's commonplace. But if a terabyte is not enough, then think of an exabyte. Okay, just we can always have more data than we could store in memory, or at least we could imagine it. Now, if we have that much data, of course, we have to be able to store it somehow. So we could still just put it on a hard drive, and a hard drive is nothing more than an extension of the memory of your computer. And so we could treat that hard drive like extra memory that the computer gets to use, and we could still use a balanced tree. We could, for instance, use an AVL tree or a red-black tree. Okay. The problem is that if we did it that way, we need to start taking into account the fact that disk access is really slow. You may have heard about the memory hierarchy of your computer. Closest to your CPU are caches, which are small bits of memory, like on the order of a few hundred kilobytes to a few megabytes, that are very, very fast. And they're made to be very fast so that whatever your CPU is doing right now, it can store that information, that data, those instructions very close to the CPU so that it can operate very quickly on those things. And main memory is a little bit further out than that, and it's very fast, but it's slower than cache. And further out from that, of course, is the disk. And further out from that is perhaps the internet or the cloud, right? And so you can think of all these things as layers of memory, and the further they are from the CPU, the slower they are. Well, disk access is many times slower than main memory is. And so if you're thinking about a balanced BST like an AVL tree that has n nodes, it's going to require on the order of log base 2 of n disk accesses. So if we had, if n was 2 to the 40, which is roughly a trillion nodes, then that means that every time we go to the disk, we'd have to pick out a new node and then decide whether we go left or right. And then we have to go back to the disk and pick out a new node and decide whether we go left or right. The height of the tree is going to be log base 2 of 2 to the 40, which means we have to go to the disk 40 times. Now, 40 times going to the disk, ideally, we would like to do it fewer than that, right? The speed of access for this data structure is going to be really dominated by the number of disk accesses. So the central question then becomes, how can we reduce the number of accesses to the disk that we have to do? And one simple answer is we can reduce it by making the tree wider. Right now we're talking about a binary search tree. If we made the tree wider, like a 3-way tree or a 4-way tree or an 8-way tree, then the entire tree would collapse a little bit because we're storing more data per, if we're talking about a 4-way tree, then the root has 4 children, and those each have 4 children. So at level 2, we're already at 16 nodes, right? And that's growing faster than a binary tree. So for instance, a 4-way tree, a tree where every node can have up to 4 children, would require, if it was balanced, log base 4 of 2 to the 40th instead of log base 2 of 2 to the 40th. And that's log base 4 of 4 to the 20th, and that's 20 trips. So if we change this from a binary tree to a 4-way tree, we would cut in half the number of disk accesses, and that could be a significant savings. And if we doubled the number of children again to an 8-way tree that again is balanced, then it would require log base 8, which would be 10 trips to the disk. Okay, so that would be a significant savings over a binary tree, just because going to the disk is very expensive. The question is, how wide should we make this tree? Well, this is where B trees come in. how wide should the tree be? Clearly, the wider the tree is, the larger each node is going to be, because a binary tree has exactly one key and two children. But if you have an m-way node or an m-way tree, it has to have m pointers to m children, right? A binary tree has two children, an m-way tree has m children. And in order to discern which of those children we should go to, we have to have not one key, but we have to have m minus one keys. So, if I have a three-way tree, for example, I have three children, 1, 2, and 3. So I have 3 pointers, which means I need a key here and a key here, 2 keys to discern between this child, and this child. Okay. So if however many children I have to have one fewer keys than that. And that means that in order to store a node that has, say, 3 children and 2 keys, I have to store all that information. That's one extra key and one extra pointer compared to a binary node. Well, let's start thinking about how this applies to disk access. Every time we access the disk, a computer operating system accesses disks in terms of what are called disk blocks. These are units of size that the operating system is dealing with when it talks to the disk. And the operating system is unwilling to transfer data usually in smaller amounts than a disk block. And usually that's around 4,096 bytes or 4 kilobytes. So the point here is if the operating system or your program reads anything from disk, no matter how small it is, even if it's just asking for 1 bit or 1 byte, the disk is going to read and return at least 4K of data, or in other words, the size of the disk block. Okay, so you ask for an AVL tree node, which might be a few kilobytes, and what it's going to return to you is 4,000 kilobytes. And you say, I didn't ask for 4,000 kilobytes. And the disks and the operating system and the disks say, well, that's just how we're going to operate because it's expensive to go to disks. So we might as well go out, grab a bunch of stuff, and bring it back in as long as we're going to the disk. And this is what's known as spatial locality. It's exploiting an idea called spatial locality. The idea of spatial locality is if you're going to access a point in memory or a point on the disk, you might as well bring in the next byte or the next several bytes, because if you're accessing address X, it means your program is likely to access address or position X plus 1 very soon. So we might as well bring that in, and then we have it prefetched and we don't have to pay the cost of going out to get it again. So this is a general idea known as spatial locality, and this is one of the reasons that computers operate with disk blocks, because we believe that if you're going to access some bytes on the disk, you're probably going to be accessing other bytes that are close by. And B trees exploit this idea. They're going to make the tree wide enough to just barely fit inside a disk block, because if you're going to read the disk, you're going to bring in a disk block, you might as well bring in as much information as possible. If the B tree was smaller, and when we say smaller, we mean having fewer children, fewer keys in the node. If the nodes for a B tree were smaller, we would be wasting space in the block. We could have fit more nodes. We could have made the tree wider by fitting more information in a block, but we didn't. That would be wasting space, and that would be making the tree taller than it needs to be. And if we made it larger so that it could not fit in a disk block, then every access to the disk to get a node would have to grab more than one disk block, and that would require more transfers. So the idea behind a B tree is make the nodes wide enough, an M-way node wide enough such that M is large enough so that it just fits inside of a disk block. Okay, so here's the logical structure. Again, if we have M pointers, 1, 2, 3, 4, up to M pointers, right? Then we have M minus 1 keys per node. So this structure right here, this is a B tree node. Okay, and so are the 3 down here. This is a B tree node, this is a B tree node, and this is a B tree node. Okay, each of these has M pointers and M minus 1 keys. Now they might not be full. We might not need not all. Just like a binary search tree, a node might have only one child. Here we might not need all M pointers for a node, but we can use up to M pointers per node. Okay, But the point here is that a B tree node, each of these nodes is going to be just big enough to fit inside of a disk block. Okay. Now, another idea to save space so that we can make the tree wider and shallower is that we're going to put as little information as necessary to search the tree inside a B tree node. So suppose that we're storing a database of people and it's searchable by name. Okay. Where does the B tree store that data? Well, what do we mean by that data? Well, we know that we need to store the names in the nodes of the B tree because that's what we're searching for. We go to the root and we search by name, and then we go to one of the children and we search by name, and then we go to one of the children and we search by name. But the name is not a person, right? A name is not the full record of a person. A person has an age and an ID number and some an address and a phone number and that sort of thing, right? So where do we store the people, the full records of the people? Well, B trees store full records only at the leaves. These internal nodes, the ones that I've been showing you, they store only the minimal information needed to search the B tree or the node. And in this case, we're talking about names. So each of these, in our example, each of these keys would be a name, a string, but they would not be the full person record. In order to get the full record, you have to always, in a B tree, go all the way down to the bottom of the tree. So you have to search all the way to a leaf node, no matter where, even if you find this name that you're looking for in the middle of the tree somewhere in an internal node, you have to keep going all the way down to the leaf node to find the full record for that person. So every successful search must end at the bottom of the tree if you want to retrieve the full record. And what that means is that we can pack, since the keys are small relative to maybe the full record, we can pack more keys into a node and into a disk block, which means we can make the nodes wider, which means we can make the tree shallower. And it also means that if you wanted to have the same data searchable by different information, like you might search people by name, but you might also search by ID, then you could build two different B trees on the same set of records, on the same set of people. One of them is searchable by name, so that's one B tree. The other is searchable by ID number, so that's a different B tree, completely separate structures, and they both lead to the same set of records at the bottom, okay? And you don't have to duplicate that information. Now let's talk a little bit about how B trees maintain balance. Well, when one thing I didn't mention is that a B tree has M children. Okay, we know that, but one thing that I didn't mention is that it has to have at least M over 2 children. Okay, in other words, a B tree node is not considered useful or full until unless it has at least half of its nodes being full. Okay, and there are special cases where, like, if the root node is not full, then that's okay. But this M over 2 is a threshold that you want to pay attention to. That's what I'm saying. So if you insert into a B tree, and that insert propagates down the tree, and you put it in some node, and if that causes a node to have more than M children, then what it does is it splits that node that has more than M children into two nodes of roughly size M over 2 each. Okay, we have M children or M plus 1 children. We can split that into, say, M over 2 and M over 2 plus 1 children. When that happens, of course, splitting a node causes its parent to have now 2 children where there used to be 1. And so that could cause the parent to have more than M children, and that might cause the parent to split, which might cause its parent to split, and so on. And so this may cause splits further up the tree. Okay. If a remove causes a node to have fewer than M over 2 children, again, that threshold, then we do one of two things. Either we look at the left or right sibling of the node that has too few children, and we steal some keys and pointers from it. So we steal some of its children, if that's possible. Now, that is possible if either the left sibling or the right sibling has more than M over 2 children. But if that's not possible because the left and right are both equally empty and they both have m over 2 children, then you could take this node that has too few children and merge it with either its left or its right child, or sibling rather. And that merge causes the parent, which had 2 children, to now have 1 children in its place, and that could cause it to have too few children, and that can cause merges further up the tree. But this is the basic idea. It's a kind of a nice idea for how splitting and merging and rebalancing works. Okay. Now, overall, B trees still have log n height, so they're asymptotically as fast as any other balanced tree. But their real speed is in how they use the disk well, and the fact that they're maximizing the width of the tree and minimizing the height of the tree. So they have to go to the disk as as often as they must, but no more than that.